it's a very urgent. You know, if you know, even myself, you know, I'm looking here to it. So, you know, I'm going into my Blackboard, you know, here, Blackboard. CBB, maybe I can share with you my screen. Here is Scalpoli, right? My CBB. Here's the thing. I just do double authentication, whatever, on my watch. It's an information. Yeah, here. Pump, fast. And you know, here. Computer slow anyway. Blackboard. Then I go here in the Blackboard. 4304, right? So if you look at it, you know, learning units, right? You know, I'm going here in the syllabus. Everything recorded, you know. So here is the syllabus, right? We learned the PWM, we learned the VHDL with discrete system, we learned the VHDL with simulation, we learned the synchronous, asynchronous. I'm gonna, you know, I told you about PWM. I need to go through the SPI I2C, but just like, you know, theoretical, because we don't have a processor. And then, you know, we can build some units. And, you know, I already give you that every single group has its own unit, right? Every single group has its own thing. I'm gonna show it to you also if you don't remember. And here's the materials that, you know, I used so far. And here, look, exam 1, 25%, March 10th. Exam 2, April 14th, 25%. The project, 25%. And then the lab experiment, all the lab experiments you're making for the lab, I will take the whole them and I take 25% of it and I put it here. And that will be your 4304 lecture. That makes sense? So there is no final. Your final is the project. You guys see what I'm talking about or no?
Yep.
So it's clear, right? Think about it. We are 4,000 level. You know, I'm not gonna go give you exam and all this. You know, if you give me something running and you justify it to me very clear, it's enough. You know, months from now we will be working in a company. You know, I mean, majority of you for sure. Now, you know, if also you guys don't remember, but you know, I'm sure that you remember that, you know, I already here in one of the thing in the time of the January 31st, I told you, you know, the groups, right? Here I say group A, names of the group, and you know what topic. Group B, what topic. Group C, what topics. You guys remember this or no? Hello?
Yep. Yep.
This is your project, the 25%, right? So you have to work from now on, you know. I thought you guys are already almost done or something. You know? Here. Of course, you know, you're gonna use some stuff like, you know, now you're gonna push data from UART, for instance, you know, you're gonna push it on a VGA, you know, you push it from the VGA back to the UART, whatever, you know, we have on the board, right? Anyway, back to the point. So I know that some of you heard about the VGA from the other courses like 4305 or whatever, right? You guys know that there is two different type of what? Of monitor controls system. You have digital and you have analog. The digital is HDMI and DVI. Analog is VGA. Everybody know that?
Yep.
Okay.
Yep.
So, you know, of course,
Professor,
digital, yes.
is SDI, is that digital or is that analog? I can't remember.
It is actually digital. Okay. The only analog is the VGA.
Got it.
And the VGA made by IBM, by the way. Those IBM guys, do you know that the only company in the world have the biggest number of US patents is IBM? They are the winner of all of the patents ever in the whole entire world. IBM. Have you guys heard about IBM, right?
I guess that makes sense. They're a pretty old company.
It's not about old company, you know, Canon, you know, whatever, Samsung, they're old also. But, you know, IBM somehow, they're freaking smart. I don't know what's going on in their head, but, you know, even they're beating the crap on Intel. Even Intel is like, it was the monster of building processors for generations, right? All of the normal computers using Intel, right? Of course, AMD was trying to do the best and, push with Intel. They didn't win because, the heatsink stuff. Have you heard about the heatsink story? I think I told you guys about it, right? Hello?
No, I don't think you told us about the heatsink story.
Okay, so the heatsink, right? So, when you buy, how many of you heard about Micro Center?
Yeah, Micro Center?
Yes.
Yeah.
This is basically, my Disneyland, When I get tired, I just go Micro Center, Anyway, so, Micro Center, when you go and decide to build your own computer, right? You go buy the motherboard, and then, you buy the right chip which supported by the motherboard, and you buy the heatsink, and, you buy the fanning system and all these things, right? Intel, somehow, their physicists, the people who work in physics departments, they figure out the best way for like distributing equally the heating system exchange on the chip in a way that the chip will not be fried. And they actually very famous with that. Any competitors that try to build processor like Intel, they failed. AMD failed with building this. And that's why in like maybe 20 years from before, or like 10 years ago, anybody buy AMD, it's cheaper, but then people just like get rid of it and just go buy Intel. Like in Pentium and Pentium 1 and 2 and 3 and i3 and i5 and i7, all of those guys very good on what dealing with the heat because of their heat sink. Then there was a very nice research have been made by have you guys heard about an institute called EPFL?
No.
Okay, it's in Switzerland. Switzerland, their biggest universities, which is higher than even MIT, is called ETH. In German, they call it ETH. And then the other one is called EPFL. Those are the biggest institutes in in Switzerland. Those guys build a new system for cooling the chip down by making holes in the chip and pushing pipes inside the chip like a thread. Like you are threading the chip, you know what I mean? And you push liquid inside. So that will cool down your chip. Who actually were the pioneer actually used this technology? Intel. Then AMD disappeared for a while, and then they returned it back. And somehow they figure out solution for the problem, which is heating. And they start beating the crap on who? Intel. You guys also aware that Xilinx got been acquired by AMD?
No, I didn't know that.
AMD acquired Xilinx 16 weeks ago for like $42 billion.
Who owns AMD?
AMD, it's a Canadian American company.
Oh, and Xilinx, I thought are they a Chinese company or?
No, Xilinx American company.
Oh, I didn't know that.
Here is a story. You know what? Not everything is just like coding. You also need to know because it's a 4,000. Here's a story. The biggest company ever work on building something reconfigurable. That means it has switches. Two companies, who? Altera and Xilinx. Okay, Altera and Xilinx started historically in 1984. Both of them started at the same time. Okay, the tool in a software programming Altera is called Quartus. What's called Quartus. The tool historically was used in Xilinx for programming Xilinx was called ECE. Then there is a professor from UCLA. You guys know UCLA, right?
Yes.
UCLA, there is a famous professor, his name Jason Kong. He came and he built a startup company, and this startup company built Vivado. Then Xilinx loved Vivado. They acquired Vivado. Then they adopted Vivado to be the official software and the retired ISE. So far so good. Then Intel wanted to change the whole entire chip market. Instead of building fixed IC and make it CPU and stuff like that, they wanted to involve FPGA inside the CPU, and they called this chip what? Broadwell. So they acquired what? They acquired Altera for $16.7 billion 7 years ago. Now there is nothing called Altera. It's called Altera/Intel Inside. Make sense? Look, can you guys see my screen, my camera?
Yeah.
Do you see this big tower of boxes in the top drone?
Yep.
Those are actually gift from Intel Altera. All of these boxes have the replica of the Nexus 4, but for Intel, and they worth like around $45,000.
Wow. So does Altera still make products that are separate from Intel, or does Intel just swallow
It has to be
up and
Intel.
bury
It's wallet.
their-
It's wallet. Exactly.
So they don't use any of Altera's IP; they just bury it.
Exactly.
Oh,
So
wow.
there is actually the team of Altera. They call it actually the research Altera team merged inside Intel, but it's still using the title Altera.
Got it.
But you know, parentheses Intel inside, something like that. You know, even Intel actually give me something which is really crazy. You know, they give me like a board of FPGA with PCIe Express Serial Communication Protocol. Each one can be using something is called HBM, high bandwidth memory. And this one can be used for actually cloud computing. Each one worth $35,000. This one, I'll show it to you. I need you to know all of these things because it's not just like coding. Coding, there is a bunch of code in internet. One second. This one. Maybe I can move get this. Because FPGA is not just like Nexus 4, and that's it, I see the rest need to be admitted. Okay, and so if you look at this, here's the board. Look, this is an FPGA. Everybody can see it?
Yeah.
Hello? Can you guys hear me?
Yeah. So that goes into
Can you hear
the.
me or not? Can you hear me? Hello?
Yeah. You don't have your headphones on.
I cannot hear you guys. What's going on here?
Professor, your headphones.
Interesting. Let me see. Why I cannot hear you, but you can hear me, right? Your headphones? No, I don't have the headphones.
Then
Wait.
you just need to switch the audio system.
Professor, put your headphones on.
Let me see.
You can hear us now, right?
This
Can you hear us?
Microsoft thing is scheiße. Anyway, can you hear me now?
Can you hear us?
Yeah, I hear you now. I don't know. I need to fix this docking thing from the Surface. It's
Okay.
computer. Actually, I hate it. Anyway. So this is actually, look, this is actually an FPGA. That's used to be Altera, but they put what Intel. Look. This is a $35,000. I need to find a computer for it because I never seen this on any computer. So anyway, so this is not just like, I'm writing code and VGA or UART or whatever, we are using PCIe. Have you guys heard about PCIe? PCIe, it's actually, the version came from PCI. And the PCI is using network topology. Have you guys heard about network topology? Have you guys studied TCP/IP?
A little bit, yeah.
So there are 7 layers, right?
Yeah.
Right.
Exactly. There is 7 layers there. There is actually a very famous freelancer from Israel. His name is Eli. And actually, Eli has a very famous website. It's called Zilibus. Have you guys heard about something called Zilibus? So you need to search for it here. It's called Zilibus. Let me show it to you because that's really interesting stuff, Great stuff, don't worry about it. But, I care more about, some information. Zili. bus. That's made by Eli. So, you know, here I can just like give you the information. Here, everybody have a copy now from Zelibus. You can look at it in the chat. It has all the possible driver in Linux and Windows. And also you can actually contact Eli, and you know, he's from Haifa. And you know, you can contact him and he can actually provide you with more information. Like, you know, how can you access stuff? How can you work with stuff and stuff like that. You know? And of course, you know, Eli is using what for communication? Huh? Somebody can tell me.
Slack.
FIFO. He's just using FIFO. So he connect the stuff with FIFO. Like for instance, I give you example. Do you remember the UART when I talked to you about it in RX? We connected FIFO. Do you guys remember that? You remember the code I shared with you? Yeah, that's a FIFO thing. Anyway, I don't want to steal your time, but you know, back to the point. So 4304 is, or you know, it's focusing on what you know how to use VHDL. You know already how to use VHDL. You don't need to know everything semantics or syntax, you know, for the VHDL. Eventually, you're gonna learn it. The whole idea: how can you search to find it, and then how can you use it in your to solve your problem? That makes sense? That's the whole thing. So we learned the UART. Now we're gonna talk about the VGA. So if I go here, oh, before I go VGA, sorry. Is there any other companies working also in the FPGA than just Xilinx and Altera? Yes. This who is working on this? Have you guys heard about a company called Microsemi?
Yep.
So Microsemi been acquired by Microchip. Have you guys also heard about Microchip, right?
Yeah, they're the ones that make the
microcontroller. Yes, yes. And actually, they got acquired by company. You know, I used to work for Atmel, and now they actually acquire Atmel. They are making that mega stuff. Anyway, so Microsemi. Oh, I made a mistake. It's called Microsemi. It's actually, they remove it now. No, it's a point still. You know, they have a website, but it's a part of Microchip. See, they put here Microsemi, Microchip. So they build also FPGA, but this FPGA used for what? Used for the space application and defense applications. Jeff, you're gonna work for space, right?
Yep.
Look, you need to know this. So space application and defense application, their software is not Vivado. Their software, which is almost like Vivado, is called what? Diamond. Which is doing the same thing. You write RTL, you make a simulation, you go into the synthesis, placement, and routing, and you will generate bit stream. This bit stream is not dot bit, it's gonna be something else, and you deploy it on the chip using JTAG, everything will work fine. Okay. NASA, for instance, you guys have seen the new rover on Mars, right? The new rover on Mars having FPGA. Can you imagine that? And this FPGA is made by who? Broadcom. Have you guys heard about Broadcom?
Yep.
It has a processor from Broadcom associated with FPGA and is used to map what? Something is called flight software. Have you guys heard about something called flight software?
A little bit here and there.
So the flight software, I have actually team, you know, NASA give me money for this. So flight software is a software act on the top of the Linux and recording all of the mission process, like recording the telemetry information, GPS informations, you know, LiDARs, whatever you can imagine. It will record it and send it to the ground station. And then the ground station will do analysis, and then, you know, we'll call back the flight software and return it back and forth. And that's actually famous for people who build drones. Have you, any of you built drone before?
Oh, a little bit. Not a full drone, but I was having some problems with the balancing and everything, but got close to building it.
What about the rest of you? Anybody of you tried to build a drone for your own?
I've done some work with like Pixhawk and
Pixhawk, yes.
a little bit of coding for autonomous ground vehicles and stuff like that.
Yes,
That's
yes.
about it.
Yes. So basically, I'm working with drones. You know, I'm a part of a competition running by NASA. It's called NASA Mines. I don't know if anybody from this was me, but some of the students. But anyway, so in NASA Mine, we build drones actually docking. Like drones will just go physically dock like this. And then they will start, charging itself, charging from each other. Like, have you seen the F-16? While, charging it, while it's flying? Same thing. But anyway, so there is two different controllers. Those controllers using ARM processors. One is called Pixhawk, as Jeff was talking about, and the other one is called Navio 2 or something like that, which is like a shield go in the top of Raspberry Pi, and you will just programming it. I think I have it somewhere here on one of the drones here. I put it in the top here. Anyway, all of those guys are very cheapy. Pixhawk, Jeff, there is a statistic say that most of the Pixhawk have been sold coming from different vendors outside the United States have a low quality. Guess what we can do to actually change this Pixhawk? We can use what? FPGA. Because guess what? All of the ports on the Pixhawk communicating with the sensors using what? UART. So the UART you learn is actually inside. So the code you wrote in VHDL or Verilog or whatever you learn can be used for SoC or Nexus 4 if you put like a RISC-V on the top and communicate between of them, and you can build your own flight control. That makes sense? I'm just trying to show you the importance of the UART when you learn. Okay?
Makes sense.
Yes. Now VGA. VGA is what? 2-dimension, X, Y, right? I have a sheet, and every single sheet is the following. Please look at my hand, and then I will draw it in front of you on my iPad. I have a sheet like this, right? There is like, how to say, the layout of the sheet, there is an empty area here in horizontal and vertical, right? And then, whatever you can write in the middle. And you just need a counter to set how many times it will be off, and then how many you're gonna be start writing, or how many will be off, and how many you're gonna be writing, and so on. And of course, we learn how to write counters using VHDL, right? And that's it. How many signal inside the XEDC are dealing with VGA? We can look together on the VGA. So let me just stop here, and I will find my VGA open project. 1 second, because I'm trying to open my project because I wrote the code. I don't want to waste your time, so I wrote the code open. So desktop, NASA, don't forget about NASA. NASA courses 4304, and then I go into the spring week 10 supporting material VGA VHDL open. Okay, now I'm gonna share my screen to show it to you guys. Everybody can see my Vivado, right?
Yes.
Sorry, it takes some time, I hate Windows. I cannot handle Windows anymore, Scheiße. Whatever, it takes some time until we can finish our discussion. So anyway, once it will open, the whole entire trick for VGA, what is the right maximum frequency you are using? And we solve this problem using what? PLL. Do you guys remember PLL?
Yeah, it's a dual clock.
Yes, that's it. See, you guys know everything. It will take some time. report status. Anyway, take some time. So if I open here the constraint file, you will find out that there are the packages for the UART. So let's search. So I have here a bunch of switches, that's fine. And I need to find the VGA. Can you guys see VGA? 7-segment display, buttons. Those are the PMODs. VGA, look. So in the VGA, it depends on the ADC. So you have actually analog to digital to analog converter. Do you know that, right? Because we are talking to analog interface. There is something in the software, in the hardware design, is called digital to analog co-simulation. So that means I simulate the analog while I'm pushing data from the digital. That is called co-sim. We are not taking this here because we need a license, a specific license for our model sim to accept, and we are using the education now. And the education will just allow us to simulate digitally. We cannot simulate analog also. Here in the resolution, we have the most, if you like to represent color in digital, you have 3 different colors. From those colors, when you mix them together, it will give you whatever color you want, which is called RGB. You guys heard about that, right?
Yes.
Red, green, blue. And if you mix with any recipe of RGB, you will get new color. That's good. So, we have 4 bits for each of this color hooked by the DAC, digital to analog converter, on the port of the VGA. I don't know where's my port of the VGA. If you open the blue one, you will find actually pins inside. So you have here the red, you have the green, and you have the blue. Are we done? No, we are not done. Still, we need 2 signals inside the VGA as an analog. One is synchronizing the horizontal, one is synchronizing the vertical. We need to be sure those guys are on, off, on, off, on, off, so we can send signal to the whole entire sheet on the screen saying that I'm ready to present anything I want to present. So that's from term of the physical content, or connecting to the analog. So everybody now aware of this, right? We have 3 different colors and we have 2 signals. One is synchronized for horizontal, one is synchronized for vertical. So far, so good. Okay, look. Now, if I go ahead and I open my laptop, my tablet, I'm sorry, and I share with you whatever. Okay, anyway, so now I'm gonna go into my Zoom, join, open. Sorry about that, my nose is not doing good job. So then you can set. And then I say share screen, and stop sharing. Huh? Okay, everybody see my screen, right? This is robotic language, so don't worry about it. I will tell you about it later if you guys would like to know. Anyway, now we're gonna go here, VGA. No, one VGA driver. I have some materials. I will send it to you later on the. No, just write VGA, VHDF or something. HGL. One images maybe that will help. Oh, here, look. Everybody can see the screen, right? Maybe I can open it like this and you guys can watch. Continue. That's basically what I was telling you, right? So the screen itself, it has hidden area and it has the active area, right? This is the active, look, this is the active, the display time. Did you see the display time area? So we need to produce, if you guys can see, we need to produce the signal high for the H sync, and then counted the display. And then after that, we will count something that's called front Porsche. And then we're gonna count the synchronized pulse to be low. And then, we will return it to back Porsche. And then, we will return it to the next line. So we're gonna take it horizontal, 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 horizontal. We're done with horizontal, we'll take the second vertical and you move forward. Then you do the third one, horizontal, horizontal, horizontal. Then you're gonna make another vertical. Then we're gonna return it back to scan all the horizontal and so on until you will end up, and then you will start from the scratch. All of this happen in the background of the VGA. So if you look to the vertical, look at the vertical. It has the same thing. Have you noticed? It has what? It has the back Porsche. It has the pulse, sync pulse, which is actually going low, and then gonna go turn it back to be front Porsche. Best way to implement this is what? Somebody can tell me. What is the best way to implement this? Counters. You guys agree?
Yeah.
So my question, so far for everybody, does it make sense what I'm saying?
Yeah.
So Jacob said mostly, but what about the rest? I need to be sure everybody's online so I can start sharing codes.
Yeah, it mostly makes sense.
Yeah, so have you noticed, look at carefully to the thing that's in front of you now, right? The rectangle, which is say display time, this is the one I see by my eyes, and I see that I'm talking to you, and I see you guys, and you guys see me. That makes sense? While whatever is called blanking time, which is basically that area, like L, flipped L or reverse L, that's actually completely dead. I don't see it, and you don't see it. You understand what I'm saying? Those actually for the reprocessing the analog part. Sounds good? The number of the front Porsche and the back Porsche and the synchronized pulse and the back Porsche and all of these things, those are pre-calculated. Are what? Huh? Pre-calculated. That means it's actually based on the resolutions of the display time. So do you guys remember when you go into a click right display setting in your Windows, you already have a bunch of what resolution setting? Do you agree? Every single one, it has its own front and synchronized pulse and the back Porsche for the horizontal and vertical. Do you know that? So those are like, written in a book. You're not inventing. You're just taking it from the analog people and applying it there. So the best way to do it is to actually use what? Generic for VHDL. Let's see what is this I'm talking about. So if I go again and share my screen here, everybody can see my screen, right? So if I look at it very carefully, here is the VGA driver. Everybody can see my VGA driver, right? Hello?
Yep.
Yeah.
In the VGA driver, my intention is to run in a 640 times 480 resolution. Huh? 640 times 480 resolution.
That's the native VGA resolution.
Yeah, that's basically the lowest one. But if I would like to keep it changing, I have to change all of the values here in front of you on the generic. See, we are not inventing anything in VHDL. We are just using generic. That's it, right? So in there, these numbers you will find in a wiki. I'm gonna send you all of these links. There is link. It has all of the numbers you can imagine. Then, here, for instance, because I'm 480, 640, I have to extend the horizontal, counting all of the Porsches and all of these things. So 640 actually is 800. And the 480 is actually 512, including all of these things, you know what I mean? And from there, you have the horizontal back Porsche, the horizontal, front Porsche, the sync pulse, and the vertical things that, if you guys remember from the picture that I was sharing with you in a couple of minutes ago. So these are the numbers. And of course, if you look into it, you will see the numbers calculated. Like for instance, HP is basically the 128 plus 16. So that's why it's 144 and all these things. How can you do this generic? That's not really hard, right? Either that you're gonna make parameters as input, or you just make it generic like this, right? Now, the time of the things. So basically, as a matter of fact, my module is basically has a clock. It has a reset, right? Because I'm running in frequency, right? Sequentially, basically. And I have all of the things that are outputs. Do you guys agree? What outputs? I have the H sync, the V sync, and also the colors, like, red and green and blue, RGB. H1, it was actually from the XCDC, it was 4-bit, right? And I have something that's called video on. What is video on from your point of view? It's a flag telling me I'm in the display time rectangle. Why I need this? Because I activate the sheet. Now I need to start drawing on a sheet, right? So that the video on can be basically connected to block memory or something. It has a screensaver. Then you just boom, turn it on, and then the screensaver will be starting moving in front of you on the screen. I know that Eden gave you in 4305, for these people took 4305, how to connect that VGA driver with a microBlaze as a microcontroller, and then you can start writing some C code and start moving stuff, right? Did you do that with you, Jeff? And I think Johnny, right?
Yeah, we did that in 4305.
Yeah, with the system Verilog, right?
Yeah, so it's system Verilog and the microBlaze, the microcontroller, not the microprocessor.
microBlaze microcontroller.
Yeah, we kind of built part of the MMIO system for it.
Yeah. For us here, we are doing everything for a nice tip machine, which is more difficult, but it's actually helping you to shape your skills. Okay. Now I decided to make the counter is counting 10-bit because I'm reaching 800. So 800, if you lock to 800, make it 10-bit is better for you because it's gonna be 1024-bit, right? Now we start also defining some of the temporary registers because I don't want to hook it directly. I like to make everything in a temp, and then I will push it to the IO. This is my strategy since we started even, right? The VHDL. Then we're starting with the horizontal. Do you remember I told you we're gonna go horizontal, 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 horizontal? We finished, then initiate one vertical, then horizontal, 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 then initiate second vertical, and then horizontal, 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 initiate the third vertical. And we keep doing this until we close last vertical, then you return it back again, horizontal, 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 start vertical, and so on. So here, if you notice, it's a sequential circuit, right? So I'm saying that if I'm resetting, so basically this is asynchronous reset. Do you guys agree? Is it synchronous reset or asynchronous reset?
Asynchronous.
You can make it synchronous. It's up to you. How can we make it synchronous?
Move the reset check inside the rise and edge check.
Exactly. See, now we are just using whatever we learned from VHDL, right? Anyway, so I'm resetting the register and also resetting the enable coming from the vertical because I need once I finish all the horizontal, I have to initiate one tick, say vertical, start counting one. Then, you know, if the clock happened, I'm counting how many horizontal happening. And I'm saying that once I reach the maximum, start from scratch, basically like, you know, you're sitting rounding the counter, right? And from there, because I reached the edge, go please turn on the vertical. That's why I make the VS enable equal 1. Other than that, just like what? Keep incrementing the horizontal, increment, and don't touch vertical. That makes sense? Then I'm done with my process of the vertical, horizontal, I'm sorry. Now I'm going into what? The edge synchronization, because you know the signal of it's called edge sync, right? That edge sync, it will be equal 0. And after the certain registers, which is basically the back portion, when I want the sync to down, right? I have some numbers I already set up. This number can be up. I make it 128, you can change it to be one of the generic. And I say, you know, don't make sync equal any number because, you know, I haven't done it. But once 128 happened, which was 0 to 127, basically, make the synchronization equal 1. So this is the signal called edge sync in the XDC. Then I start counting vertical, right? Because I finished horizontal 1, 1, 1, 1, 1, 1, 1, like that. Now, the vertical counter is equal 0 because I reset clear. So when I set clear, have you noticed? The vertical here will be 0 and horizontal here will be 0 because this is called parallel processes, right? Those two processes are sharing parallelism in the reset. Do you guys agree? Huh? Hello?
That makes sense.
Yes. So now, if the vis enable is 1, that means I finished the first scan of horizontal happen. I will start looking on the maximum vertical happen. If the maximum vertical happen, do what? Reset, that means round back, because you have to do this all the time. It's like continuous. Then if else, you know, just count. Just count when enable is 1. That's guarantee every tick happen, the counter will be incremented, which is aligned with my story. You know, vertical, sorry, horizontal, 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 horizontal. I reach the button, then I will go up, increase the vertical 1. Then again, horizontal, 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 horizontal. I reach the button, oh, vertical 1 time, and then horizontal, 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 and so on. Then I need to generate the H, the V-sync. The V-sync is coming from the sync pulse, and the sync pulse in the vertical, it's actually less than 2. That means 0, 1 in the 640 times 48 resolution. This is from the timing of the manual. And now I generated the VSync. So pretty much I generated the VSync and H-sync for the VGA. After that, I need to set up the edges of the display time. Do you guys agree? Which is called video on. So there I'm actually making what? Here is the edge from this side, and the edge from this side, and the edge from this side, and the edge this side. The area in this rectangle is gonna be display time, which is basically turn on video on. That makes sense? So here I'm saying that when I reset, I don't need to see video on, but be sure that, you know, when I reach all of these combined together, that's why I say and, that means I got all of the corners. If all of the corner exists, whatever in the middle is a display. That's why I call it what? Equal 1. Other than that, if any of those guys out of this display section, make it 0. So pretty much we built what? The driver. If we just call this and connect it to VGA, it will show us that, you know, VGA will not say a screen is not found. What it will do, it will show us what? A screen just like boom, turning on like this, without anything on it.
Professor, so what is the purpose of the video on? Sorry, it actually displays something when...
No, I will tell you. Video on, it say that, you know, in there, I can do any activities. What activities? That will be the next hierarchy.
Oh, okay, got it.
But
yeah.
at least, you know, if you turn on H-sync and V-sync correct with timing, your screen will be showing me what? Just on. You know, the LED, right? The LED in your button will turn blue. That means, you know, the screen now ready to take anything from me. But how gonna take anything from me? That's why I define video on. So I can in the top build on the video on whatever I want. That makes sense?
Yep.
So what exactly I can do as an example? Screensaver, right? Or I can make strips like, you know, some lines, and I can change the thickness of the line and it change the color of the line. That's one of the possible example. So that's why I made it here. But if you noticed, you have to be sure also that, you know, with 640 and 480, the frequency that your eyes as a human visual system in your brain will accept it has to be in a certain clock frequency. 100 megahertz will not be actually, your eyes will not recognize it. So you have to go ahead and turn on PLL. So if you click on the PLL like this, doesn't like me, upgrade selected. So we're gonna upgrade it. Excuse me. Let's see what's going on in this, because you know my ears is hurting me. So let's see why you guys cannot hear me and I cannot hear you. Can you hear me now?
I can hear you, Professor, this whole time.
Can you say yes or no? Anything?
Yep, we can hear you. We can hear you.
Microphone.
Hello?
So, Professor, it's in the audio settings in Zoom.
Setting audio maybe. This computer is killing me, you know. One second. 30 seconds in Zoom can change to use your speaker instead of headset. It used to be automated. It is automatic for me. I don't know why this specific computer is giving me a headache. You know what I mean? It's too much. You know. I mean, I start hating this Surface thing. It used to be meeting closing your microphone. So. Administrator. I know what's the problem. Security problem. I have to go into the administrative. Oh, shit. Whatever. I'll find a solution soon. It's not important. Anyway, now if I look into this one, it's got upgraded. Have you noticed? Takes time. If you look here, you will find that I'm using 25.09 something megahertz. This is not defined by me. It's defined by who? Defined by the manual of the analog.
So, IBM?
IBM. So that's why if you notice, you know, I said 25.1, but because of the approximator inside the ASIC part of the PLL made it actual like that. It's because there is an error rate or error margin, but still your eyes will recognize it because within the range. That makes sense? Do you guys know that, you know, there is a bunch of universe we are not seeing because, you know, it's outside in the above level of your eye and hearing system. And there is some other stuff below our eye levels and hearing system exist. And maybe they are close to each other and we don't see them. Do you know that?
Yeah.
So that's called parallel universe. Have you guys heard about something called string theory?
Yep.
That's a string theory. So that means, you know, maybe some other creations here, you know, and, you know, we don't know what's going on. They don't see us, we don't see them. Okay, anyway, anyway, now I'm trying to build any block to get the benefit of the driver. So this is the block. This block is really naive block. What is taken as input, what is taken as output. So you already have a clock, you have a reset, and I made a switch, and this switch resolution-wise is a 4-bit, okay? Then I already have the R and G and B, and those gonna be also some switches I have. Then I have also the video on coming from the driver as an input, so that it was an output from our driver, but is input into this block, because that will initiate this block, will make it running. Then you have the HC values, which is basically output coming from the driver. Do you remember the HC and HV that I created? The counting? Those are, because that will tell me which points, because HC and HV will be telling me the horizontal and vertical definition of the pixel. So this pixel, this pixel, this pixel, this pixel. So V, HC, pom, 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 and I start sorting them. So I can make like a funny face or whatever I want. Then, you know, of course, the red and green and blue, those will be connected final into who? Huh? To the XADC, right? That makes sense? Now, let's see what I made. It's just like a silly switches with sequential. So RGB, I connect them as a sequential registers. And then I said, you know, if video on, all of this will happen. So that means within the area that your eyes will recognize. That makes sense? Then, you know, there I say, you know, if the BR, have you noticed I start using the conversion? So that means if you also remember, because I don't know if you guys remember or not, we have to use what? Arithmetic operation and unsigned, because this is unsigned data. I don't care about the sign. And also I'm using the numerical library, if you guys remember. There I say, you know, if I push the button to be 1 or 0 or 2, that will be a new resolution for the which location of the VC, which location of the counter. And that will start changing the size of the redness, or the size of the green, or the size of the blue. So then, you know, the lines will be get thicker or thinner, thicker or thinner, and combining all of this color together will make a fantastic colors. That makes sense? Okay, Luke. Hello. Sounds good. Then if I go into the top module, of course I start handling, because, you know, I don't want to keep it go into the driver by my hand and change it. So that's why I make a parameter in the top connected to the parameters in the driver. So I came here and I said, you know, what is my final IO? My final IO clock, the BTN, the reset, and the switch, of course, and the other set of switches, and the synchronization as an output, and the output of the red and green and blue. And of course, this is our values, you know, I already have from the driver, if you remember, for the 640 times 480. Then I instantiated the VGA driver as a component. I instantiated the strips, basically the component that I showed you, which is like switches with key statement, and initiated, of course, the PLL, because, you know, the whole entire thing, it has to be running in 25.1-ish megahertz. Then, you know, I start stitching everything together. And we know from the trick of the PLL, you have to lock with the clock ended together to be sure that, you know, the clock will be stabilized. And then, you know, I start putting all of the parameters here, as you can see. And of course, I hook the generic coming from the top file with the generic into the drivers. And that's it. That's actually basically the whole entire top file. If we run here synthesis and generate bit streams, we'll be able to deploy it on the chip. So I can show you from the other computer and Linux. I will pull out and connect it here so we can play a little bit. Any questions so far? Is it easy peasy lemon squeezy? Look at this trick. How many threads I have in my computer? I have 8 threads. Make all of the 8 threads running to finish this job. So basically, you know, it will partition all of the tools of Vivado in 8 threads to make it faster, to be done in like a few seconds. Now the question, where is my VGA cable? I need VGA cable and I need HDMI. I don't have any VGA cable. Hello? Are you guys following me?
Yep, but I don't think I have a VGA input on my monitor. I have a.
It's not the end of the world. There is HDMI.
And yeah, we can convert HDMI, VGA to HDMI.
Because by the way, HDMI is completely digital.
So, correct.
But then, we need to have like a compiler. Like a compiler, that means we should have what? I will use this, but this is, I use it for some special mission, but it's okay. Also, by the way, do you guys know that I can use the PMod? Everybody can see my screen?
Yep.
Yep,
Do you see
yep.
this?
What
That's
is
actually PMod for UART. I can hook it here, and I can make it the official G tag. I can hook it here. I can actually push data from there using UART, while the other one using the other UART with a different speed. There is one of the project actually I used to do with for fun, just to play, which is basically have UART here, UART here, UART here, UART here, UART here there, and make this as a router. And every single one is connected to another board. And then the other board connected to other boards. And then, you have like a big mesh network, and all of them talking to each other doing different rates. And each one, it has RISC-V processor. And then, all of those guys are talking to each other and pushing data. And I was using it for computer vision. That was a really fun project. Also, there is another thing I need to ask, because I need to know, you guys know all that. Do you know that you can also deploy the bit stream using the SD card?
So I've heard that. I've never
You've never seen it, right?
Yeah.
I will do it in front of you if you want. Basically, you have to, here's SD card, right? I will take the bit stream now, and I will put it there.
Yeah.
Then there is a jumper here. You have to change to say read from the SD card. Then automatically will load it from there, and it will not be talking to the G tag. Especially if you are actually powering up the board from here, not from the USB.
Yeah. What's the format for the SD card? What does it need to be?
FT.
Okay.
I think I have it already, but I don't know. Let's see. I'm tired. Let's see. See what I have. Okay, open my screen. Everybody can see my folder? Or you can't? What you see? You see Vivado or what?
No, just your
Folder, right?
Yeah, folder.
See, I already have UR_tx.bit. That was another example. So I can just remove this X like this, and I put it maybe in my desktop for now. You know what? I'll make it like a folder, and I call it what? UART is the card. And then I will just go. And then we just go like that. Boom, 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 boom. And it's empty, right? Then we will do like this, and we will wait for the synchronization to be done. If you go here in the runs, it's gonna tell us what is going on, because it's still doing synthesis. It takes some time. Just let me see, where can I find VGA? Where is my VGA, man? Oh,
Yes.
I don't know what exactly happened, but my computer went like kaboof. So I don't know. You guys here, yeah. What the shiza?
Let me guess. Windows.
Yeah, I don't know, but my whole entire screen went kaboof, you know. I don't know. I mean, leave it running or no matter what. I don't want to stop the whole thing, but you know, where's my VGA? I need a VGA. I used to have a lot of VGAs. What happened? You know what? I have a VGA here. You guys can see my screen, my camera. I don't see the camera is
No,
working. Huh?
I can see your Vivado, but not your camera.
Oh, really? That's a lot of fun. Okay. So where is my camera? Where is my camera? Here. Now is my camera is working. That shows that how a surface is very yucky. Anyway. And then, you know, I can put, as you said, microphone like this. Can you guys now hear me? Maybe I can stop this and then go into
I can see you and hear you. At least I can.
now speaker. What about now? Can you guys talk?
Can you hear
Why
me?
I
Testing,
cannot hear
testing.
you?
Testing, testing. 1, 2, 3. Can you hear me? 1, 2, 3. Can you hear me? 1, 1, 1, 1, 1.
Pretty sure he can't.
Yeah.
Yeah, right.
Yes. Finally. Okay. Now we need to find. So everybody see here, right? This is my VGA. I have it to be also HDMI. If you have HDMI problem, I can do it for you. Okay. Here we go. Now I return it back to screen. I share a screen. Everybody can see now how many lookup table I use. 31 lookup table. How many flip-flop I use? 34 flip-flop. It's not really hard to calculate it. Do you want to see how to calculate it? Huh? The calculation came based on what? Those. You have 10, 10, 20, and then this 10, 10, 20, you already have those guys. It came into the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. So we have 4, 4, 12. Yeah, so 20 plus 14 is 34. Yes. So it's 34. Okay. So anyway, if I go ahead and connect here the VGA. This. And I think I have a power here, different power. Let's see. Here's the power, which is basically, everybody can see it, right? Here's adapter power and here's USB. So I can just go ahead and put USB here. And then I need to power it up, but after I put the SD card. Anyway. Is routing. Have you noticed something, guys? Hello? Did you see the flip-flop increased? Somebody can give me a reason why.
What did you change?
It's not a change. It's actually the tool. So, you know, the tool is doing something called routing, right? What does it mean, routing? It's connecting point to point, right? Okay. Switch to switch. And how it works is like, you know, horizontal, vertical. There is no way for you to connect diagonal, right? Yeah. So the tool figured out that it will be cheaper than taking more time to find 34 is to add extra one in the middle, without it changing your timing requirements. That makes sense? So this is the tool decision. Kiduk? That makes sense?
Yeah, it's just a decision made by the
tool, because this tool is based on genetic algorithms. It's a type of AI,
okay.
artificial intelligence. But of course, there's something in the FPGA which I don't think it will be covered by undergrad, which is something that's called partial reconfiguration. And there is another one, it's called dynamic reconfiguration. Have you guys heard about it?
Sorry, one more time.
Partial reconfiguration versus dynamic reconfiguration.
Oh no.
So in the partial reconfiguration, the FPGA look like a sheet. So, you will start breaking the FPGA into portions. And then, you will make a constraint in this portion and say that this design has to fit in this portion. Don't ever talk to the others randomly. Then it will be considered like a mini FPGAs inside the FPGA. And we use something for this called floor plan. Have you guys heard about it? It's called floor plan. Did you see that? The timing never came negative, which is a good sign. So all of the timing here, WNS, TNS, WHNS, THNS, TPWS, all of those guys are associated by, two of them associated by the setup time, two of them associated with the whole time. And nothing is negative. That's actually a very good impression. That's, everything is perfect, fine. If it's negative, then we have to redesign something or lower the frequency of the maximum frequency to meet the timing. So there will not be metastability issues. Okay, doke. We are now toward the bit stream. And what we can do, we can open here and we turn it back to desktop. It used to be courses. And inside courses is the 204304, 4304. And 4304, I will go here in the spring, week 10, supporting material, VGA, VHDL, and I'm looking for what? For the .bit file. So here I'm looking for .bit file. So .bit. Here. Everybody can see it? Hello?
Yep.
So have you noticed the file .bit has the name of the top? Do you guys agree? Look, VGA underscore strips underscore top automatically generated to be the same name .bit. So I will go here and copy this, and I will go on my SD card. So I'm gonna go here in my PC, and there I have the USB drive, and I will dump it there. So now I have the bit file on what? The SD card. So I'm gonna unplug the SD card, and I have it there. Take it here, and I put it where? In our SD card here. So you just put it there. Are we done? No. So we need to find the jumper saying that, SD. USB underscore SD. And from there, we need to power with external. So we're gonna go ahead and take this power and connect it to my power supply. So now everything is powered up. Everybody can see it. There is a power there. Is it powered up? You look, the power. Okay, now we need to find, it says busy. You know why busy? Look, busy. Why is busy mean? It's actually trying to read the bit stream in the SD card. Once this busy will be cleared, we'll be able to talk to the screen. So I'm actually gonna turn on the screen in front of you guys now. I'm waiting until this busy thing will go. It's taken some time, you know. Oh, programmed. Look now. Look, can you? Everybody can see my point here. You know, the light's too much. Can you see this light is what? It's green, right?
Yeah.
Now see my screen.
Okay, yeah, you got some color bars on there.
Yeah, based on the switches we have, look, I can start changing the resolution and it's changing the size of every single line based on the combination of the what? The switches I already defined. That makes sense?
Yep.
So far, any question? Oh. Is there any question?
Not for me.
What about you, Jeff?
I was actually wondering if you could go back really quickly to the code that was actually drawing the lines. I wanted to take another look at that.
We can return it back to, you know, this code, you know, you're gonna take a copy of it, right? So which one you want? So this one, right?
Yeah, I was trying to kind of make sense of what you were doing in here.
So what I'm doing, you know, the switch value will be a point into the red. Have you noticed? So you already have a 4-bit in the red, right? So what I'm doing, actually, I'm reading locations. So that means I'm changing the value of the red. You got it?
Yeah.
That's why I see I concatenate. You know, this is how you concatenate in what? In the what's called? In the in VHDL. So you remember in Verilog, you guys make the curly brackets, right? Curly brackets, and then, you know, in the middle, you're gonna make comma, 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 and you put everything. Here we just make, like, you know, the sign of and. And it's a 4-bit, right? So that's why 1-bit, 2-bit, 3-bit, 4-bit. And basically, I'm telling you the bit location based on the SW as an integer value. Make sense?
Yeah, thanks.
Yep. Okay, any other questions? Any concern? Any problem? So let's summarize what we learned. Today, in the beginning, we talked about the technology and other people, how to use technology. And, you know, all of this Verilog or VHDL we are learning is a piece of cake versus some other complicated stuff, right? And we talked about the vendors and, you know, communication protocols. And then, you know, we moved the gear into the VGA. We figure out the VGA is an analog interface. So that means, you know, you need to write a digital interface co-signed with the analog interface by designing the timing issues, fixing the timing issues using counters for defining the horizontal and vertical behavior with associated number coming from the manuals and the VGA designers. Then we built the VGA, which is just turning on the screen with ability to write something in the display area, which is a rectangle or whatever, you know, you can call it rectangle or square or whatever. And from there, we start putting whatever we want. And that specific example was strips with, like, changing the size of the strips and the color of the strips. And we figure also out that, you know, that display time is based on a clock frequency, and that's actually also designed and constrained by the manufacturer. Then we learned that, you know, we can actually program the FPGA also with other different way, which is basically SD card. And we just need to replicate or change some of the jumper setting, and also, you know, powering up the board. We can power it up still with the USB cable or just external powered up. And I did this in front of you. And then we have a full demonstration on the screen, as you can see. And I want you actually to look very carefully to the screen. You will find there is an empty area there in the side, right? Can you see this empty black side?
Yeah, because your monitor doesn't scale it. So
Exactly. So we have to scale it somehow. And that's actually opening the door to do a reconfigurable VGA driver. And I don't think it's a difficult thing. It's actually a piece of cake. Somebody can tell me an idea. How can we make it reconfigurable?
I think that would have to do with the whatever the sync characteristics that you get from the monitor. So there's a handshake that the monitor sends out that says, "Hey, this is my native resolution, and I can support these sort of things."
Yes.
If you don't adhere to it, then it's gonna look weird.
True. So the only way to do it is basically to make a scanner saving all of the HP back push, front push, whatever, horizontal, vertical, and with all possible numbers, and then it will do a scanner on a memory, scan and say fixed.
Oh, that's called EDID. Sorry, I'll put it in chat.
Yeah, makes sense. And instead of fixing it as like a generic like that. Make sense? Any other questions? Any concern? If there is no questions, I would say that at least it's enough for now, so at least you guys can digest what's going on. And next time I can show you also how can you deal with data coming from block RAM into the VGA to display something. And then, all of this has to be start using, guys, for your project, because, don't forget the project is the main thing. And we already have defined the project and everything from the January, right? Sounds good, everybody?
Yeah.
Yep.
Super. And I hope that you guys are already fine with the first exam. Let's hope that, the second exam will be also better. And from there, we can talk more about, how we're going to deal with the grade. Okay, Luke? But at least I did whatever I promised. And I promised that, the last questions, all of you guys will get the grade, which is a final grade.
I appreciate that. Thank you.
Thank you. Okay, if there is no question, I want to say thank you for your time and for the effort and for attending this course. And, it is really enjoying that, to talk to you guys, and it's really fun to work with FPGA because I love FPGA. And I hope you guys actually like FPGA, you're not afraid of FPGA. And we can continue on Monday for the other examples. So they're going to strengthen your knowledge. By end of today, the recorded version of this lectures will be posted on the Blackboard associated with the same code that I wrote here for the VGA, and any other materials I will find about VGA I will be posted as well. So it's gonna help you under the week 10, under the learning unit of the course Blackboard. Thanks a lot, guys, and have a wonderful rest of the day. And I'll see you on Wednesday for the for the lab. God bless you.
Have a good day.
Have a good day, Professor. Thanks.
Thank you.
If we
God
didn't
bless all
have
of
any
you.
available slots for office hours, can I just see you after office hours?
After office hours, I will be home sleeping.
Okay, so
So, either that, we're going to make it on tomorrow meeting, or,
we don't
if
have a
it's
meeting
coding, if it's
tomorrow.
heavily coding, you can post the stuff on the Slack, and let's see what happens. Have you checked the internet?
I've gone up and down, left and right in the internet, and a lot of people are having problem with it.